Welcome everyone to session 19 on plane stress. In this session, we're going to have the opportunity to cover Mohr's circle. And learning Mohr's circle is almost like a rite of passage for a mechanical, aerospace, civil, biomedical engineer, whichever type of engineer might be using some form of mechanics. And once we're done with this session, we will have covered how Mohr's circle is derived, its method of construction with some examples. So part 2 will focus on elements, material elements that we can rotate and transform to be able to look at in-plane principal stresses and max in-plane shear stresses. And the third part will focus on examples with structures. Okay, so once we've completed this session on Mohr's circle, have an idea of how Mohr's circle was derived, how to apply it to material elements, and then how to apply it to material elements embedded in material structures. So for the first part of this portion, where we're going to get into the derivation of Mohr's circle, I'd like to just review a few slides and items that we've covered previously. 2 sessions ago, session 17, we discussed how we were able to take an element and rotate it and then get a different set of stresses that describe the state of stress in that particular orientation. And we also described how we might look at the sigma x prime stress coming off of a face, okay, that's been rotated by some angle. We discussed how it's often a good idea to use exaggerated triangles so that the opposite is much thinner or smaller than the adjacent side of a triangle. We then moved on to deriving some general equations for plane stress transformations. And once everyone saw these, they were like, no more doing the equilibrium about the triangle for rotated or sliced element. And then in our last session, we discussed how we were able to determine max or min in-plane shear stress, and we were able to determine max, min, in-plane principal stresses, and this is useful for being able to think about how a brittle material might fail. And then in the kind of second portion, or maybe not second portion, but we kind of spread it out. In the other parts of session 18, we also discussed max in-plane shear stress. Okay, so this is important for being able to determine how ductile materials might fail. And so we'll cover more of this when we get into failure criteria in the future. So we have equations that are able to kind of tell us, hey, how much do you have to rotate to be able to get into this state of maximum shear stress, and what are what is the maximum shear stress, and what are the normal stresses that would be coming out of the element as well. And they're the same, and they have an average, as we see here. Okay. So that's these previous sessions kind of set the stage for what we're going to discuss next, which is Mohr's circle. So Christian Otto Mohr was an engineer, and he liked to use graphical methods to describe mechanical phenomena. And he came up, building on other people's work, he came up with what we now know as a method of visualizing these transform stresses in the form of a circle. Okay, and so this technique is very powerful, and even though this circle doesn't look like this element or this element, when we were plotting in the past, for example, the normal stress versus rotation angle, or the shear stress versus angle of rotation, we kind of got an idea, right? These are sine and cosine type waves, sinusoidal, and so they're cyclical in nature as we look at the relationship between the normal stress and the shear stress. So let's first, in this portion, go through the derivation, right? There's a lot of stuff drawn here, right? We are familiar with these diagrams already, okay? But this is something completely new. But let's go ahead and take 2 or 3 minutes to go about how Mohr circle is derived. So we first start with 2 of the equations for transformations, from sigma x to sigma x prime, and tau xy to tau x prime y prime. Okay, so here's one of them. This is the one going from the sigma x and sigma y, tau xy, to sigma x prime. And from these sigma x, sigma y, tau xy, to tau x prime y prime. Okay, so there's 2 equations. We then can bring them together, okay, actually we haven't brought them together yet. We're just reorganizing the top one, okay, as you see here. And then now we're going to bring them together. We're going to square and add them. So take these 2 quantities, square, and add. And this is what you get, which is a little bit messy. But it can simplify to this equation, okay? So what do we see here? Well, we saw, okay, we had some cosine and sine, and we're able to get these things to simplify, okay? And the left side stays the same as what we have here. And it doesn't look like much, does it? It's like, well, how do we get a circle out of this? Well, let's take a look at things. We know that the equation of a circle, right, can have like an x minus xc quantity squared, right, quantity y minus yc squared equal to some radius squared. So that's kind of what we begin to see here. We see, okay, if this sigma, okay, becomes an axis, and we say that this quantity right here is some offset from it, okay, that starts to become a descriptor of maybe where the middle of this circle is. And this also has some input on the graph, okay, so this y-axis ends up being based on tau. And we just discussed how there's an x offset from the origin with this term. This tau, actually, there's just a -0 term. So this y-axis, or the circle, always ends up being on the x-axis, right, at y equals 0, because this is 0. So then what's this over here, this whole thing over here on the right? Well, this is going to be the radius squared, okay? So that we have now this term right here as an x offset, which is actually average of sigma x and sigma y. Inside this x, or this, virtual x, which is really like a sigma, okay, minus this quantity squared, and this term, right? So the center of the circle ends up being at a sigma average comma 0, as we see here. And the radius, this r squared, is connected to this right hand over here, and we take the square root of it, or if we plug this r into there, which is squared, it just becomes this term that we have right here. So now we have kind of a familiar equation that describes a circle. And it's in terms, the parameters are in terms of stresses that we might see on a material element, right? We have our sigma x, right over here. We have a sigma y. Over here, we have a tau xy, describing the shear stress. And what we haven't really described too much is what happens with angle. Right, so first we have equation of a circle with these terms. And notice they're not any they're not any angle terms here. Okay, but we've drawn an angle. We can somehow swing around, and we'll get into this in a little bit. Okay, but for now, the two things to pay attention to are that we can draw a circle. It has a center given by sigma average comma 0, and it has a radius given by the square root of the the difference between x and y, the sigma x and sigma y divided by 2 squared, plus this tau squared term. Okay. Now, one thing to keep in mind is that there are different conventions in different books and different websites for how Mohr's circle is constructed. We, as we kind of just showed there, and I kind of skipped, that we actually use this tau going downward. Okay, this is positive tau. So if I have a value down here, like it's not minus 10 megapascals, it's going to be 10 megapascals on this bottom portion, okay, underneath the sigma axis. So we follow that convention where positive tau is going downward. And if you look at this Wikipedia page, there are 3 conventions, 1, 2, 3, okay? And we're using the second one where tau is positive. Now, it will become maybe a little more clear as we go, but we end up having the angle of rotation on Mohr's circle, this 2 theta here, going in the same direction as the material element is actually rotating by putting it down this way. Now, if you use this convention number 3 with tau upward, you can have that as well, but it's a little bit strange because these shear stresses then are said to be giving the opposite direction of rotation as we normally think. So normally we think Z is coming out of the board, so this shear stress is going to be on the top. All right, this one will be giving a negative into the negative Z direction. This one on the side, which is really our classic tau xy, on the X face in the Y direction, that's giving a positive. So this convention number 2 allows us to keep kind of equilibrium and rotation, or the lack of rotation as we understand it. And it allows us to also keep the rotation as we transform the element in the same direction as what you draw here. Okay, so this is what Hibbler uses, and this is what we're going to use in this course. Well, it's been a few minutes, and we have now a question based on the derivation and based on kind of our introduction to Mohr's circle. If you have a material element and it has a state of stress, sigma x, sigma y, tau xy as given, or with different numbers, how do we figure out where the center of Mohr's circle is and what is the radius of Mohr's circle? Okay, so go ahead, take a few minutes, run this problem, then come back for part 2.